Hey there. Good morning, everyone. Thank you all for being here, and thank you guys for hosting me all layer. My name is Rahul. I'm the co-founder of Connext. For those of you who have not experienced Connext yet, Connext is a protocol that has been around for a really long time. So the company actually started in 2017 when the crypto market looked very different. So we started out doing very different things. Always the focus was around building good, secure, scalable infrastructure with the end goal of onboarding more users onto Web3. So really that has changed over the years to initially focus on scaling and now focus on interoperability. And the interesting thing is scaling and interoperability are really like two in the same thing because when you have scaling, you're offloading transactions to something else, whether it's a secondary layer one or a layer two or a layer three or whatever. But unless you have that interoperability, the scaling actually doesn't do anything on its own. So anyway, the title of my talk is the HTTP of Web3, and this kind of defines the future for Connext as well as the interoperability space as we see it. So just to kind of take a step back here, let's time travel a little bit back to the 1980s and see what the early stages of the internet looked like. So back in the old days of the internet, you had to do a lot of manual stuff and really like interact directly with infrastructure. So you had to like know basically the subnet of some network that you wanted to connect to, use telnet to connect to a server. Then you had to like FTP some storage off of it. And it really was a very manual process that exposed a lot of these layers to the end user. And this is because there was kind of a mishmash of different protocols and other kind of like a lot of other things that you had to kind of think about and do manually. So then we fast forward to today. So today it looks very different. You have rich interactions that you can do with very different pieces of infrastructure under the hood. So let's say YouTube is an example. YouTube will send network requests to this very well-defined, very robust networking stack, and it will be able to query content from CDNs and deliver that to a user. It will be able to go to its storage locations and get data. It will be able to query other servers through APIs. So the whole stack has been very much like abstracted, well-defined, and it's very expressive. And the reason for this is because of HTTP, right? HTTP is basically what made the web composable to some extent. So bringing us to what the Web3 is like in the 2020s. I don't mean to kind of pick on Aave here, but if you go to something like Aave or basically any of the Web3 dApps that are pretty big right now, have this property where you have an app that is multi-chain, deployed on many different chains, rollups, whatever, and you have to manually interact. You have to pick what kind of network you want to connect to. Then it's going to go to your wallet, and it's going to tell your wallet you need to change to this network, and you have to kind of manage all that stuff. So really, this feels like dial up in the internet where we had to like manually turn on our internet and connect to some website by SSHing into some server or something like that, or using telnet or something. So it's while it's very cool and there's very cool things we can do and we all love Web3, this is definitely not the future. This is not how things are going to look in the future. And not to mention in this case, like all the liquidity is kind of fragmented. You need to think about bridging funds from one chain to another chain if you want to use a product on that chain. So then we fast forward to how things look today, or sorry, not how things look today, but how things will look in the future. As all of us are here because of this roll up as a service day and alt layer is kind of pushing this vision, I think we can all get on board with the fact that the main interaction that users will have in the future is with app specific layer threes. So I strongly am a believer that a lot of things will move to different siloed layer threes where they can kind of control more mechanisms around things. So you'll have like a swap layer three, you'll have a lending layer three, Uber and Airbnb eventually are going to become peer-to-peer applications that live on their own layer threes. And then you'll have storage and decentralized compute that are also running as like decentralized services. And our vision for the future is that all of these will be connected by an interoperability layer, which will make these interactions extremely abstracted from the users themselves. So then how do we get to this vision? Really, we need to define this kind of interoperability layer as a modular layer that is fully specified and standardized. So with this, then we can really start to build the infrastructure that makes this type of stuff possible. So let's go back to the internet and say how the networking stack looks in this modular vision. So the networking stack is already modular. So you have a transport layer, which is TCP. You have a security layer, which is TLS. And then you have this application layer. And this is important because the application layer is really what allows everything to be composable. It allows developers to build new apps. It allows content to kind of be linked to each other over the internet. And it allows users to not have to deal with any of this. They can just go into their browser and start browsing. So then how do we translate this vision back into interoperability and Web3 in the blockchain? So what we can do is we can kind of break the pieces down into like very similar looking pieces. So what you have is you have a transport layer, you have a verification layer, and you have an execution mechanism built on top. And let's dive in a little bit and explore what each of these layers do look like. So the transport layer is the very base layer of this communication between different blockchains. How do you bring a block header? It can be any payload, but let's just say it's block headers because as we'll go into later, this is the most efficient way to transmit data from chain A to chain B. You know, this may seem easy in like an all EVM world. You just have some kind of relayer that's just like reading data from one chain and putting it on another chain. However, this will get more and more complicated. And one of the things I really believe is that a lot of these app-specific layer 3s will end up moving away from EVM into, you know, more highly customized, different versions of VMs that are highly tuned and efficient for their own use cases. So, you know, then you need these kind of adapters to basically bring this EVM-based process that we have right now to be able to be translated into any type of transportation. So what I'm saying is we already have an extremely well specified and battle tested transport layer protocol. It's called IBC. So those of you who know IBC, it's basically a Cosmos based system for transporting messages and doing this whole process of transport between different blockchains. If you've looked into it, it's extremely well specified. It has multiple clients running it. It's basically like extremely well documented and it's battle tested because it's being used across many different blockchains for a very, very long time. And that's what you need with these type of infrastructure projects. So that's for the transport layer. So then we move on to the verification layer. So a verification layer works like, how do you prove that something, like whether it's a block header or something else, is valid from chain A to chain B? So this can happen in a various number of ways. The bottom line here is that verification mechanisms are going to be commoditized and be an open marketplace. So this is going to be like basically an open marketplace where different actors can compete on speed, cost, and chain support. And since basically, if you boil this down to the fact that you're just sending block headers from one chain to another chain, this is like a fixed piece of data. So the cost is not going to scale with the amount of data that you're sending. So it's really going to be kind of like a race to the bottom and an open marketplace. And the other thing to note here is that there's a lot of teams working on this right now. There's a lot of really smart people who are trying to solve this problem of securely verifying data from one chain to another chain using ZK proofs, using light clients, using message aggregation, etc. And these people are very focused on this singular problem. So they don't care about transport, they don't care about execution. All they care about is verifying that a piece of data from one chain is properly is valid and usable in other layers of the stack. So then that brings us to execution. So this is a very important piece of the puzzle. I do apologize because I had emojis and things that don't seem to be showing up on this presentation. So some of these diagrams look a little weird, but you know, I can point people to the slides later. So anyway, execution. So after a block header, we go through the transport process, we go through the verification process. Now on chain B, we have a block header that has been verified. Then how do you build rich interactions on top of that? So this is where we really get to the HTTP analogy, because really like doing something with this block header and root is the hard part. Once you have this, then you have a ton of infrastructure you need to build to actually like build apps, build cross-chain interactions. So the truth is application developers don't want to deal with this lower level stuff. They don't want to submit proofs. They don't want to read data, things like that. The data so then like this is also where the costs in the flow are, because when you're consuming this data cross chain, you're actually like consuming a lot of data potentially, because you're going to be sending like a big Merkle proof that needs to prove some kind of data and then building complex interactions on top. So the bottom two layers do not really have much value where, you know, users are going to be paying a lot of fees or something, like I said. So that's why these are going to be really like highly commoditized and really like kind of race to the bottom. But the application layer, the execution layer, this is where you kind of have a little more room for the flow. And really execution is what brings us cross-chain composability. Like without it, you can only consume data across chains. But really, when you have this, you can actually create applications, build rich interactions. So like to bring it back to the web analogy, the web is a graph of hyperlinks between content, and it's independent of the links under the hood. And that's really where we need to get to with this blockchain as well. So what we say is this execution layer is global state composability on the interchain. And what Connext is trying to do here is we're trying to focus in and build a really well-specified, generalized, extensible execution layer framework. So then that breaks it up here a little bit. So now at the transport layer, you have teams that are specifically working on this exact problem. Like Cosmos is doing all the work around building the base layer for the specifications around IBC. Polymer is a team that we're in touch with that is building IBC everywhere, basically. So we want to let them focus on that problem and, you know, eventually like build a client that will plug into that. Similarly, on the execution layer, you have these really great teams, some of which are mentioned here, which are, like I said, laser focused on solving this one problem. They don't care about anything else. Like we talk to a lot of these teams. They're not trying to build like full bridge functionality. They just want to build these verification mechanisms that allow you to move things from one chain to another chain and prove them very specifically on the destination side. So at the execution layer, this is what we are focused on at Connext. We want to focus on building the ability for developers to interact with verified cross-chain mechanisms. And you know, if you look at this from the big picture, you'll see that a lot of bridges are trying to build this entire stack. So obviously, if you try to focus on too many things at once, you're going to end up like compromising on things and not really being able to deliver the entire solution to users. So that's why we're really trying to laser focus on this one part of the stack, which is the execution layer. So then when you have an execution layer, what are the things that you can do with it? So this is the most basic use case of an execution layer, or of the execution layer, is to do a write. And I'll call this a slow write right now, and you'll see why later. So what you can do is a user can make an X call, which is a call that is meant to go cross-chain from chain A to chain B. And this assumes that the block header has already been sent to chain B. So after some time of making this X call, this block header gets packaged up, it gets sent to chain B through the various transport verification mechanisms. And then at some point in the future, you have a root a block header that has been proven on chain B. So then your execution layer mechanism will do all the computation to send a proof that the user's transaction is actually within that block header, and then it will execute any type of data or call or funds transfer or anything. So the use cases for this are around things like secure cross-chain messaging, managing governance, things like that. Things where you really need a very secure mechanism for sending messages across chain that may or may not include value. So the next part of this is a fast execution mechanism. So the reason I call this fast is because you have this verification process and this transport process, which can be actually very slow because, when you're dealing with this type of system, there are going to be a lot of things that these protocols are going to do to reduce their own costs because, at the end of the day, these are kind of like race to the bottom protocols that won't have much margin. They might be even public goods. So they're going to try to like reduce the cost as much as possible for that reason. So what that involves is a lot of batching. Then you have these things like ZK proofs, which might be really heavy and take a lot of time to run. So at the end of the day, you're going to have to, this process from sending a block header from chain A to chain B is definitely not going to be an instant process. But something you can do is you can have something called a fast execution layer. So what this is doing is this is listening for this event on chain A. And because it sees the event on chain A, it has a certain guarantee that this block header will eventually be received on chain B. So it knows at some point it can prove this. So then what it can do is it can actually go up front and send a transaction on behalf of a user. So let's use like an any-to-any swap, for example. So what that means is a user is going to maybe swap on chain A, then send the funds to chain B, and then do another swap on chain B. So what this fast execution layer can do is it can do the swap for the user and send the user directly the output of that swap. And then, we'll have something in this execution mechanism to understand that this is what happened, and then have this fast execution layer be able to claim the funds back after this block header has been proven. So this is kind of like the use case where you get with many like cross-chain bridging right now, where you want your funds immediately. You don't want to wait for some execution mechanism to happen. So this is what enables that. This is what enables an instant, like really nice, clean user experience. So cross-chain swaps, like any-to-any swaps are a really good example of this. Cross-chain zaps, fund movement. And then the other interesting thing is you can also do things like verify a signature. So if you have a signature that can be verified from chain A, then you don't need to wait for the block header because you can already see that that's going to happen and verify that on chain B without needing to wait for a block header. So then the other really interesting mechanism is a read. So say you have these block headers that are coming, they'll be coming on like various intervals. Then you want to prove some data against that on chain A itself. So really all you need to do, this shouldn't be an X call, this should be an X read. So an X read is where you're just going to still submit the same proof for a block header that you already have and prove that something has happened on chain B. So say you have an oracle that's like updating price data every 30 minutes or whatever, or every minute or however much they send their thing, then you have all that information in a block header that has been sent. So once that block header is received here, then you can read it immediately, and you can basically read data from any chain, anything that has ever happened on that chain. So other ways this would be useful: read gas price data, read token voting power as well. That's a cool one, right? Because you can basically read what your VE token balance or whatever is at any kind of snapshot in time after you've received the root on the chain that you have your DAO on, for example. So yeah, I've referred to this a few times, but XCall is basically how Connext is envisioning this whole execution layer process starting. So this is basically a primitive to facilitate asset and or data transfer across arbitrary chains. So it's designed to mimic Solidity's built-in call method. So what we want to do is we want to make the process for developers around making these really expressive cross-chain interactions extremely easy to build. And since it mimics Solidity's built-in call method, they don't really have to think about much or know much beyond what they already know in Solidity. And here is basically a snapshot from the code about exactly how you would do an XCall. So it's really simple. As you can see, the parameters are very straightforward. You have some kind of fee that you pay to the relayers for sending this amount. You have like a destination domain and target, token address. You have some safety fallback parameters around the message sender, the amount you're sending, slippage, because bridges will have some kind of slippage and things like that, and then you have call data. So this is basically the bare minimum amount of parameters that you can have to be able to make really nice kind of cross-chain interactions. So, one thing I'll get at here is that specification and standardization is positive sum. I think a lot of companies might view this as, eating into their bottom line, or this kind of like goes against what normal companies want to do, because normal companies, they want to control everything. They want to, close their APIs. If you look at like Google, Twitter, Facebook, things like that, like they're all charging for API access now because they're built like companies. They want to make profit. But if you look at what the end user wants, the end user wants truly open APIs where anybody can compete, use the APIs. Like if you look at the example of Reddit, this is a great example right now. So Reddit had all these different like clients and user interfaces built on top of it because it had an open API. But now that it's shutting down its API, it's been a huge backlash because, a lot of these apps are being forced to shut down because they can't consume the APIs right now. So what I'm saying is that like we want to get to a world at Connext where everything is specified, everything is standardized. This might make our own protocol like, less profitable, I guess you could say, because it allows competitors to just come in and build multiple clients. But that's not what we care about. We care about making it a better place for the actual end users to interact and, be in this world. So, just to reiterate that, Connext is not a company. Connext is a public good. Because we're building Web3 infrastructure, it needs to be something that is given to the public. It's given, deployed, and it is usable by anyone. So it operates on this standardized playing field where anybody can come and operate and build tooling around it. So, I like to say this a lot, but, at Connext, we don't want to compare ourselves to Apple, Google, et cetera, like that. We would rather hold ourselves to the bar that Ethereum holds themselves to. Like Ethereum is the ultimate vision of a public good that has been realized. And, if we could all be like Ethereum, I think we would all be pretty happy. So, just to wrap up and recap here, these are some thoughts that I want to give here. So standardization at all layers of the stack encourages competition and a race to the bottom, which is better for users, right? So obviously, if all the companies are competing in a perfectly free market, they are going to always undercut each other until they're making the minimum amount of profit that just allows them to survive. And that's how Web3 is built. Web3 is built so that there's no middlemen, there's no rent seekers, there's no people trying to like take a cut. There shouldn't be any of these cuts. There should be, zero fees. Zero like protocol fees should really be a race to the bottom and not even exist in a lot of projects. Right now, I think there is protocol fees, but that is something that is getting slowly undercut. Then we need to break things down into modular pieces. So modular pieces allow standardization and specification, and they allow, like I was saying, they allow the best teams to focus on specific parts of the stack and really kind of compete on cost and speed and what matters to them. They get to focus on like one really small piece of the stack and really kind of build it out the best way they can possibly build it. Then execution application layers are what make protocols composable. So this is where we want to focus on at Connext. This is how we want to be able to interact with developers, interact with users, and make end user interactions possible and good. And then to end it all, Web3 infrastructure is a public good. I strongly believe that these are not companies that are being built. A lot of the other teams, some of the other teams are definitely acting like companies, trying to make profits, trying to figure out how they can increase the revenue as much as possible. But I strongly believe that Web3 infrastructure at the end of the day is a public good. And it needs to be compared to Ethereum. Like I said, Ethereum is the ultimate public good, and all of these companies should be striving to be more like that. So thank you all. That was the end of it. And yep, I will make this presentation available everywhere.